Okay, second to last video, 9.3, improper integrals. When I teach improper integrals, I normally start with a conundrum, a little problem like this, where I ask students what the trouble is to find a certain problem. If you want to try to figure out the trouble yourself, pause this and give it a try. It's not too bad. All right, so the question is asking us to find the area of the region in the first quadrant between y equals e to the negative x and the x-axis, this area here. Since I'm finding area, it's very clearly going to be an integral. Integral is starting at 0, but then it's never ending. E to the negative x never reaches the x-axis. So as I add up this area, I'm never going to have an end point where I say, hey, take the integral from 0 to 27 and stop there. Like, there's never going to be a stopping point. So essentially, I'm finding the integral from 0 to infinity. Some students will say it's not a problem. Since this is going towards infinity and it never reaches the x-axis, there must be an infinite amount of area there. So they just say it's infinity. That's not necessarily true. You should be careful of that logic. We've seen sums before that had some limit, right? That didn't go towards infinity. Things like 1 plus 1/2 plus 1/4 plus 1/8, right? When we did geometric sequences way back in pre-calc, we found that when we added those up, that didn't go towards infinity, even though they're an infinite number of numbers. That added up towards something that got closer and closer to 2. Area, when I'm doing integrals, that's just a sum. It's a sum of a bunch of rectangles. So it's quite possible that when I add up all those infinite number of rectangles, I'm going to get something like this, which approaches some limit, right? Some end value. And so to do this, we're going to have to make use of something called improper integrals. So 9.3, improper integrals. Up until now, we've been finding integrals over closed intervals. Sometimes we can find integrals whose limits of integration approach infinity. These are called improper integrals. They look like this. So if I wanted to find the area here that I was alluding to before, from e to the negative x starting at 0 going towards infinity, I want to find this integral that starts at 0 and goes all the way towards infinity. That's called an improper integral because infinity is not really a number, and when we do integrals, we normally have it going to some closed interval, so like 0 to 252. I don't care. If there's ever an infinity showing up here, it's an improper integral. You might have already guessed how we're going to solve this based on my conversation back here when I started adding up 1 plus 2 plus 3, 1 plus 1/2 plus 1/4 plus 1/8. I said that gets closer and closer to 2. That was when we were talking about limits, right? So if I wanted to find an improper integral, one easy way to do it is to rewrite this integral as a limit. Instead of saying the integral from 0 to infinity, we can write this as the integral from 0 to b, and just say, hey, let's find what this integral goes towards as b goes closer and closer to infinity, right? So I just want to find that limit of the integral from 0 to b of this, right? This is not a problem. We can definitely do that. We know how to find integrals. You take the antiderivative, you plug in the b, plug in the 0. Doing that antiderivative of e to the negative x is negative e to the negative x. I'm going to evaluate this antiderivative from 0 to b, right? Those are my limits, which means you plug a b in and you plug a 0 in. And so really I want to find the limit as b goes towards infinity of this thing, because this thing is going to tell me the area there that starts at 0 and ends at b, wherever that happens to be. I don't want b to end. I want b to go towards infinity. So I just got to figure out that limit. Just like we've seen in the past, this negative exponent notation tends to be really helpful when I'm doing calculus, right? It makes this antiderivative easy. When I'm doing algebraic work, it tends to be easier to rewrite it. So that's the step I'm going to do here. I'm going to rewrite this. Instead of negative e to the negative b, I'm going to write that as negative 1 over e to the b, because e to the negative b is like putting that e to the b in the denominator, right? Minus a negative e to the 0. Anything to the 0 is 1. So minus a negative 1 becomes plus 1. And then when I look at this, I say, well, as b is going towards infinity, I've got negative 1 over e to the b, which means this thing is getting bigger and bigger and bigger. But negative 1 divided by something getting bigger and bigger and bigger is going to get smaller and smaller and smaller, which means this limit is going to get closer and closer and closer to 0 plus 1, which is just equal to 1. which is kind of weird, I always thought, because this is the area under the curve e to the negative x. Oops, sorry, this is a typo. That should say e to the negative x, not e to the negative x over 2. My apologies. But this is what I was trying to find. But if this was e to the negative x, that area under there is 1, which is just kind of a nice, clean answer. I find it weird and kind of cool. All right, that's the essence of today. We're definitely going to throw a few more problems at you that are a little bit different, just so you can see it, but that's essentially what we're doing. This one isn't much different, right? The only difference here is I'm finding the integral from negative infinity to 0, in which case that's the thing that I'm having a problem with. So instead of having b goes towards infinity, have b go towards negative infinity and replace that negative infinity with b, right? Then you just do the calculus. Find the antiderivative of that. Well, antiderivative of this is going to be negative x minus 3 to the negative 1. You might want to check to make sure that's the antiderivative yourself, right? But you guys know how to find antiderivatives, so I'm not going to spend too much time explaining that. The whole point of the second fundamental theorem is once you find the antiderivative, you plug in the limits of integration, the 0 and the b, and subtract. So that's what I'm going to do. Plug in a 0, plug in a b, do your subtraction. Looks kind of ugly now, so let's make it look a little bit better. This simplifies to 1/3. That's really nice. That simplifies to 1 over b minus 1. That's not bad. As b goes towards negative infinity, this is going towards, again, 0, right? 1 divided by something huge, even if it's something huge in the negative direction, is still going to go towards 0. So that limit is 1/3. All there is to it. All right, let's try something a little weird. What about this one? Something like this. This integral goes from negative infinity to infinity. So I don't have just one thing to replace, I've got 2. That can be bothersome to students. Your book didn't want to deal with 2 things. So the way your book handles something like that is they actually took this integral and they split it into 2 integrals, right? Because that's one of the properties of integrals. You can definitely split it apart. Instead of going from negative infinity all the way to infinity, they said, hey, you can rewrite this as negative infinity to 0 and then 0 to infinity. And you can write them as 2 separate integrals. Find this one using the methods we just talked about, find that one using the methods we just talked about, and you get your answer. I'm not going to do that one. That's why this dot, 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 because I figure you could try that on your own. If you want to, go ahead. Personally, I kind of like a different method for solving these. I think it just works out a lot slicker. You don't have to do an integral twice. It just seems a lot easier. And it's something you can definitely handle. Another way to do this is just instead of having one variable, saying have b go towards negative infinity, you could have 2 variables. You could rewrite this as a limit with 2 things going. Here's how you write that notation. I'm going to use 2 variables, an a and a b. So a and b. I'm going to have a go towards negative infinity and b go towards infinity. So you can definitely use 2 variables when you are doing limits, and you can have a go towards one thing and b go towards another thing. This is how you write that. I'm gonna solve this one just because it's kind of a cool one and one to keep in mind as you're doing problems. If I wanted to solve this, all right, I'm finding that limit of this integral, which means I need the antiderivative of that. This should look familiar to you. Antiderivative of that is arctangent. So since I know the antiderivative of this is just arctangent, plug in the b, plug in the a, subtract. That's the next step, right? So antiderivative of this is arctangent. So arctangent of b minus arctangent of a. I'm trying to find the limit as a goes towards negative infinity and b goes towards infinity. So I need to know what arctangent looks like. I've got a graph of it hidden right here. Here's arctangent. It's kind of a cool looking function. Remember, it does the opposite of tangent. So the arctangent actually looks like, let's see, let's start with b. B is going towards infinity. As I go towards infinity, arctangent gets closer and closer and closer to pi over 2. It's got a horizontal aspect to it there. As a goes towards negative infinity, as I go towards negative infinity, arctangent gets closer and closer to negative pi over 2. So this one actually ends up being pi over 2 minus negative pi over 2, which is just pi. And again, I find that kind of cool. Like I looked at this, the area under this curve from negative infinity to infinity is just pi. It's kind of just a cool irrational number for what this one was. The original graph for this, by the way, if I want, it looks something like this. Come on, nope. Rainbow circle. All right, it looks something like this. And so all that infinite amount of area goes closer and closer to pi. It's kind of cool. All right, we are just about done. We got to talk about convergence versus divergence. This goes back to our idea of sequences. Remember when we talked about 1 plus 1/2 plus 1/4 at the beginning plus 1/8? That's something we talked about in pre-calc. If I keep adding those up, that sum gets closer and closer to 2. So we say this converges to 2, right? We say the same thing for improper integrals, right? If I'm talking about this integral, I would say, hey, what does this integral converge to? It converges to pi. We went through all the work. We found that the integral got close, the area under that curve got closer and closer to pi. So we'd say this integral converges to pi. However, sometimes they don't converge, right? Like if I asked you to add 1, let's just say 1 plus 2 plus 3 plus 4 on over to infinity. That's just going to get bigger and bigger and bigger and bigger. It does not converge to some number, so we just say that diverges. Remember that? Same thing happens when we're talking with improper integrals. If I gave you this problem, the integral from 0 to infinity of 2x dx, I wouldn't even bother with the calculus. I would just say, yeah, diverges, done. See if you can figure out why. All right, the reason I would not bother with it is because I know what y equals 2x looks like. It looks like that line, roughly. And I know what integrals do. Integrals starting at 0 and going to infinity find the area under the curve starting at 0 and going towards infinity. And as I look at this area, that area is clearly getting bigger and bigger and bigger. And I'm just adding an infinite amount of area. That thing is clearly going to diverge and go towards infinity. You can definitely work it out if you want to. It's just there's no need for a problem like that. I think I did work it out here just as a practice. If you wanted to, you could rewrite it as a limit, right? As b goes towards infinity, go from 0 to b. Find the antiderivative of 2x, which is x squared. In this case, I'd plug in a b, get b squared, plug in a 0, get 0 squared. Subtract that. As b goes towards infinity, I've got infinity squared, right? That's going to be going towards infinity. It diverges. So when you have an answer like this, yes, infinity would be an okay answer. It's actually kind of a better answer. It explains how the integral is diverging. There's other ways things can diverge. You might remember from pre-calc, but diverges tends to be the way we just say it. We say, hey, that integral diverges. All right, last problem. Do you suspect this integral would converge or diverge? It's a good idea to think about this a little bit before you actually do the math, because if you think about it just briefly, you'd be like, yeah, this clearly diverges, and you can save yourself a lot of time. This one, I know what 1 over x looks like. It looks like this, all right? And it's the same thing over here, but I'm not really caring about that over there because I'm starting my integral at 1 and going on towards infinity. So I'm finding this area. Now, when I glance at that, I'm going to suspect that this might converge because I've got some amount of area. I'm adding less and less area as I go on, right? This is getting closer and closer to 0. Like, hey, that thing might converge. So I would definitely do the calculus to check and see if my suspicions are correct. So I'd say, all right, fine. Let's do this thing. Before I find the antiderivative, rewrite it as a limit, right? Limit as b goes towards infinity from 1 to b of 1 over x dx. Antiderivative of 1 over x, that's natural log of x. Technically natural log of absolute value of x, but I'm not bothering with the absolute value because all of my x's here are positive, right? From 1 to infinity. Trying to find the limit as b goes towards infinity. So plug in the b, plug in the 1, do your subtractions. As b goes towards infinity, I've got the natural log of b minus 1. The natural log of b, though, as b goes towards infinity, natural log is going to also go towards infinity, right? As b gets bigger and bigger and bigger, the natural log of that thing will also get bigger and bigger and bigger. It'll get bigger really, really, really slowly, but there is no limit. It's going to just keep on going towards infinity. So that one actually heads towards infinity, which means my answer for this equation, that integral, is that integral diverges. All right, that is it. Here's a summary. If you like summaries, you can jot this down. Just says for some constant c, here's the different ways you can rewrite the integrals, right? Integral from c to infinity, I can rewrite as b goes towards infinity and replace it with a b. If a negative infinity is there, have b go to the negative infinity and replace it with a b. If you got negative infinity to infinity, you can split it up and do both of these, like the book suggests, or you could just rewrite it as an integral from a to b and have a go towards negative infinity and b go towards infinity. Last note, if this limit exists, then the improper integral converges to that limit. Some vocabulary words there, right? If the limit fails to exist, then the improper integral diverges. That's it. Your assignment is section 9.4.1 in your textbook. Problems 1 through 9 odd, so just 5 problems. Have fun. See you later.